is what the calculation I did, and so now if I compare and contrast ripple carry adder and carry bypass adder, the ripple carry adder increases the delay like this, whereas the carry bypass adder, it increases slowly because of the fact that we are bypassing the carry through the masses. So where is the crossover point? The crossover point, and this is what exactly we are discussing. What should be the value of m, right? The crossover point is typically between 4 and 8, depending on the size of n. So most people kind of axiomatically they assume that n should be 4, but that's not true, and that's why I showed all those things. You may have to do simulation and all, and you'll find out that the real answer lies between 4 and 8. So the advantage of carry bypass adder, you may not see too much in your design because you're using 16-bit processor, but if you make 32-bit or 64-bit, you'll find out that this thing differs a lot actually, because the slope of this is much faster than this. So this is one way to do that. Another way to do that is what is called carry select adder. Carry select adder uses also multiplexer, like in the case of carry bypass adder. In case of carry bypass adder, the multiplexers were introduced between the chunk of ripple carry adders. So the multiplexers are located after 4-bit, 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 4-bit to basically bypass the carry. But here in carry select adder, we are introducing multiplexer in a little different way. The idea over here is that why not I assume carry is 0 and generate the values of P0, generate the different values, assuming in the ripple carry adder the first bit is 0. And alternately, I can assume that the first bit is 1, carry in is 1, and accordingly I generate the carry bits. So I do that in anticipation, and then I select one of these two when this carry appears at the multiplexer input over here. So if it is 0, it takes the value from here. If it is 1, it takes the value from here. So now I'm using some sort of a temporal parallelism of carry generation, assuming the input carry is 0 and input is 1, and I'm setting up the output values for the, and as soon as this carry comes, this is coming from another state, so this comes a little later, so I will be selecting one of these depending on the value of that, and that will be used for generating the sum generation. So this is what the concept is. So with this idea, I can now go back to the same problem of 16-bit adder. I have now the setup units, which is basically generating the propagate and generate functions. And then I have the 0 carry and 1 carry, which are so assuming the input carry is 0, so I set up all the values over here simultaneously in this block. Assuming the input carry is 1, we set up the value, and then we will be taking one of these. So we will be taking one of these values depending on the value of the CJO over here. So we do this again in a chunk of 4 bits in different blocks. So this is a 4-bit wide block in this example, but this may not be the perfect example, and we'll look into that. For the sake of generality, let us assume that this is m-bit wide, even though here we are showing 4-bit, but we assume that m-bit wide, like in the other case. So now I can write the expression for P carry select adder as P setup, which we say as TPG. Then there are n-bit ripple carry occurring in these 2 blocks. So we have m into P carry. And then I have, like in the previous case, n by m. Here there are n by m multiplexers. So I write n by m Emax. And then the final P sum, the summing operations in the last, after this comes out. So the advantage is you'll find out in the worst case carry propagation that as soon as this is computed, these muxes will be firing and the subsequent sections will be taking the values from their propagation. So when this is calculating, this is also calculating, this is also calculating. So these are all happening in parallel. Okay? These are all happening in parallel up to this. All these are happening in parallel. Now, first, this bit has to select one of these, and that will be creating this bit. That will select one of these. That will create this bit. That will select one of these. That will create this bit. That will select one of these. So, as soon as this bit is selected, one of these will be going and generating the sum. And then, as soon as this is selected, this is created, one of these will be generating that. So subsequently, you find out that as soon as this comes, after 1, 2, 3 unit of delay, the others are generated. So that's how this is quite fast also. As a matter of fact, it is faster than the carry bypass adder. And here's the example. So earlier, we saw that it took 12 units of time in carry bypass adder, but in carry select adder, you can see that 1 unit of time is taken to calculate the TPG, the setup. And then there are 4 bits are here, so it takes 4-bit M carry, which is 4 carry. So 4 unit of time in this. So after 5 unit of time, we have the values of the carry rippling through these 2 stages over here. And also in other cases. So as I told you, that all 5 will be, the upper part will be done in parallel. So after 5 units of time, you have the value ready at the input of the multiplexer here, 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 all of them. So now the multiplexers are waiting to be selected so that it can pick one of these depending on the value of carry and then pass it to the sum unit. So after 1 unit of time, which is the multiplexer delay, we'll be having the value over here. So initially, if it is 0, it will take, say, the value over here from this side. And if it is 1, then it will be selecting from here. But after 1 unit of time, which is the multiplexer delay, it will be coming over here. So after 1 unit of time, multiplexer delay, it will come over here to select this. So after 3 units of multiplexer delay, you have this one selected. So the value which are generated simultaneously after 5 units of time, it comes over here. After 6 units of time, it comes over here. After 7 units of time, it comes over here. After 8 units of time, it comes over here. But you have to add the delay of the multiplexer, so essentially 9 units of time. And plus 1 unit of time delay corresponding to the sum. So after 10